All right, have a really quick one here for you today. Last one of the quarter, Unit 6, Lesson 9, the average value of a function. I'm going to basically just show you how you can use a definite integral to find the average value of a function over some interval, and we're going to get a little intuition for what that means. Like a lot of calculus concepts, if you can think in terms of physics, it's easier to make sense of. And so we're going to start with this question here. How have we found average velocity? The common mistake here is to think, okay, average velocity, change in velocity over time. That would be average acceleration. In just like standard, like straightforward everyday terms, how fast were you going? Well, it's the change in position over the change in time, right? You know that, so don't forget that, right? It's just how fast were you going? Distance over time. And so if we use our normal notation, the change in position, we'd say this is position B, the end, minus position A, all over the change in time, B minus A, right? Versus if I wanted to find average acceleration, well, acceleration is change in velocity over time. It's the change in velocity over time, and this would be equal to the ending velocity minus the starting velocity all over the change in time. And so if you think about these here, right, these look a lot like, at least the top part does, it looks a lot like the result of the fundamental theorem of calculus. Remember the fundamental theorem of calculus, it's one of the like three things, if you could tattoo it on your body for the AP exam, you would want to, not a recommendation. It's that if you take the antiderivative at B minus the antiderivative at A, it gives you this definite integral. And so we can see that this looks a lot similar to the numerators of these two functions. And so here is, right, thinking in terms of velocity and acceleration, if you just mechanically work this out using the fundamental theorem of calculus, well, this right here, I know via the FTC is v of b minus v of a, because the antiderivative of acceleration is velocity all over b minus a. Holy cow, that is the same thing as average acceleration. And if you do this for velocity, right, the antiderivative of velocity is position. So you'd have position b minus position a all over b minus a, right? I'm getting those b minus a's from these right here. And so this is equal to average velocity. And so the result here, right, this is the one you want to have this burned into your brain. If you do exactly this, if you do 1 over b minus a, kind of refer to that as the width of the function, right? It's how far did you go, like time-wise, from a to b of some function f of x. This is equal to the average value of that function. And so let's see this in action, and we're going to see why it's useful. Let's say we wanted to find the average value of 2 plus x. And so what I mean by average value, right, I mean of f of x. Remember that this is the height, right? This is the y, this is the height of this function. So according to the formula we just found, if I want to find the average value from 0 to 3 of 2 plus x, I can do that using the fundamental theorem of calculus. So this is equal to, let's take this antiderivative. The antiderivative of 2 plus x is 2x plus 1/2 x squared, just using the reverse of the power rule, right? Always check your answers. The derivative of 2x, yep, that's 2. The derivative of 1/2 x squared, yep, that's x. And so what we have here, plugging in 3, 2 times 3 plus 1/2 of 3 squared, minus, well, this whole thing is just 0 since there's no constant. So really we just need to figure this out. This is 6 plus 1/2 of 9. And then what I forgot here was, right, this whole time, if I want to find the average value, I need to be dividing by 3 minus 0. All over 3 minus 0, all over 3 minus 0, etc., etc. So all over 3 minus 0. And I work this out, and what I end up having here, 6 plus 4.5, this is 10.5 all over 3, right, turns out that this is equal to 3.5. So 3.5 is the average value of this function. And now, what you may start to think about here is, that seemed really complicated. You're just asking me what's the average height of this line? Well, we start at 2. We finish at 5. Why can't I just say, duh, the average value is right in the middle here at 3.5. Can't I just do 5 minus 2 over 2? That only works if your function is linear. And the reason that only works if your function is linear can be best seen by thinking about, and I'll go back to the top part, think about this function here. This is x squared. If I just take the average of 9 and 0 and I look for this answer at 4.5, right? If you think about what's happened here, we're already, right, halfway between 0 and 3 is 1.5, but look where we are. We're already past 2. And so this function spends a lot more time at its lower values. So it's about how much time you spend at each value. You cannot just average these, right? So I'm telling you, this answer is not equal to 4.5. We need to use the definite integral. Another way to think about this, right, the power of calculus is that we can do this for any function. And basically what's going on is we're just using area equals width times height. And if we know the definite integral represents the area, if we can find the area using the definite integral and divide by the width, right, that's the b minus a part, right, and the area is the definite integral from a to b, that gets us the average height. And so, sorry, I forgot to replace this here. This should say x squared. And so let's just do this same process. 1 over b minus a times the definite integral. Sorry, it's not b minus a, it's 0 to 3. 1 over 3 minus 0 times the definite integral from 0 to 3 of x squared. Well, okay, this is 1/3 times, and I'm going to do my antiderivative. The antiderivative of x squared is 1/3 x to the third. I want to calculate this from 0 to 3. And so this is going to be 1/3 times, and really it's just the first one that's going to matter here because we're going to have, but I'll do it all out. So we're going to have 1/3 times, let's just say a big parenthesis here. This is 1/3 times 3 to the third minus 1/3, just so you can see this all out here. 1/3 times 0 to the third. And so this is going to be 1/3 times 1/3 times 3 to the third. 3 to the third is 27. 1/3 of that is 9. I have 1/3 times 3. The average value of this function is 3. And so if we look for where 3 hits, right, you can see that this average value here is not smack dab in the middle of this function. It is not exactly at 1.5. But what you can kind of visualize this as is that this area in red, right, is going to be the same as this area in green. Those two areas, it turns out, are going to be exactly the same if you measure it out. I know it's a little bit hard to see there, but trust me, those two areas are the same. And so the key points to remember here. The key points to remember here are that it all comes down to that this is the average height of the function divided by, the average height of the function is the area divided by the width. And if we literally just remember that, average height is area divided by width, well, area, we know, is the definite integral, the area under the curve. Width is b minus a. That tells you the average value of f of x. If you think about this in terms of position, velocity, and acceleration, this is the easiest way to remember it. If I take the definite integral of the velocity function, the fundamental theorem of calculus tells us that this is position b minus position a, right? It's the antiderivative. Well, position b minus position a is change in position. What is average velocity? Distance over time, right? Change in position, we call that distance. Change in time, we usually just call that time. And so the change in position is your definite integral, right? The change in position is your definite integral, and the change in time is your b minus a. That's the average value of a function.